speaker is Adam Sherer from Cadence. He's a product management group director, speaking from Boston. It's early morning there, so good morning, Adam. Adam's topic is unified safety and functional verification. Adam's team is responsible for the simulation-based verification technology product lifecycle management, and is the automotive segment lead for verification at Cadence. He is also the chair of the Accelera Promotions Committee that provides marketing support for the Accelera Systems Initiative Standards Organization.
Okay, thank you. I'm assuming you all can hear me. I have a relatively short presentation here to focus in on safety and verification and their relationship. Try not to repeat some of the material from my previous speakers, so I'll pass through some of that content a little bit quickly and focus on the specifics in my presentation. I presented some topics similar to this at the NMI 26262 event in March in Coventry earlier this year. This is a relatively small set of that content. So, as you've heard from my previous speakers, about the 26262 standard, the point that I'm going to focus in on here is just the elements that are focused on verification. So the standard as it exists today in the 10 chapters has a lot of information about qualitative validation. So looking for the system modeling, as a previous speaker had stated, and looking to see that you have done that work. But there's a set of data that's quantitative, where we're looking for very, very detailed, specific measurements within the standard, and that's going to continue to grow. There is an additional chapter being added to 26262 in 2018 that will focus on digital verification. There may be elements of analog verification in that as well. When we presented this topic and these points at an autonomous car event in Detroit earlier this year, back in August, the resounding information from the OEMs, the Tier 1s, the IP suppliers, semiconductor companies in that room is that the standards and the work will become increasingly quantitative over time. We've talked in previous material about the need for measurement and the need for tracking this and the need for checking across the vendor list in that design chain. That's going to increase. This is about indemnification, it's about preventing injury, but it is a measure against a lawsuit as well. And for that, we're going to need to have even more data. So for all of you collected together in this the V in the verification club, this is very good news for all of us. It's going to be an exciting time of new development, new verification engineering. So one thing that's, I think, very good that you'll see from the various speakers here is that we're all speaking the same language. So I won't repeat all the comments on safety culture. Very, very well put. The area that I'll focus in on is the quality measurement. And that's making sure that we do functional verification at all levels and abstractions for all the system elements. And we measure the safety verification responses. And that's what I'm going to really focus on in the presentation, is that the system needs to be free from undesired and unplanned events. We'll talk a little bit more about that in the measurements that come up in the next couple of slides. Documentation, again, we heard from our first speaker about the tool confidence level, and then all of this information needs to be collected together into a safety manual, and that's what we seek compliance on a per product basis. All right, so there's a comment about IP. The IP can be certified for use within a product, but compliance is on the product, semiconductor, or board level system. So the work so far has been labor intensive. In this picture, which is taken from the previous example, the functional verification side, we happily mention the Cadence tools here, but honestly, Cadence, Mentor, Synopsys, we each have successful tool suites for digital. It's the left-hand side image and analog, and the right-hand side image, and that work is, I think, relatively well done, particularly in the mission-critical application areas. We've done a lot of manual documentation, Excel spreadsheets, and other tracking systems TVS has automation, Cadence has automation in this space, but by and large, the customers we find are still doing manual requirements tracing. It's increasing, but it's something that we all need to focus on for any of the safety critical activities. Safety verification typically has been an afterthought, and I'll present on this in the next few slides as well in some more depth. But the tool environments have often required rewriting, refactoring the verification environment to be used in safety verification, and may include refactoring some of the design itself, and that's problematic. If you recall the TCL statements, we want to be able to get to a TCL 1 where we're pretty confident, or we're certified confident that we're not introducing safety violations. And when we start modifying the design by hand, it's a big risk to use that tool chain. So we'll talk about what's needed for automation there. TCL I won't address because it's been discussed. And then we have to extract data from all of this and populate a safety manual, as I mentioned on the previous slide. So this effort can run into millions of dollars per year for 32-bit microcontroller product lines and such. It can be a very expensive process. So as an industry, we all need to share together, work on automating this process. So quick on terminology, some basic concepts here. The blue, the module, that's our functional component. You can imagine from this IP within the device, there's going to be some set of functional outputs. These are the normal signal paths for data processing in our design. There's a checker, and the checker is a piece of design, and so we should not confuse that with assertions or test bench elements. These are things that have to be built into the design because they're going to either correct errors we see in the system, faults in the system, or they're going to simply report those faults to the system surrounding. We do need to do fault simulation. This is something that's discussed heavily in the standard, and we'll talk about that in the next few slides. And that's injecting faults into the module or checker to see how the system responds. So we need to determine how the faults are propagated and how the faults are detected. And I'll discuss on the next few slides why this is different from design for test. So safety and functional verification, and this is the thesis of this material, have to be one flow. And this has been something that's been cited to us in dozens of customer engagements we've had with the safety verification capabilities at Cadence. So functional verification, this is to verify the correct system behavior. Absolutely need to do this. I'm assuming that this audience is well versed in those processes. It's certainly a major topic in the DVClubs as we have them. So this is completeness in a digital and analog verification, positive testing, that's good data to make sure we have good response, negative testing, bad data to make sure the system can filter through that, and that's the normal system behavior. We also need to measure the system response in the face of faults, that is, errors that could occur. So here we're talking about not just the stuck at 0, stuck at 1 manufacturing style faults, but we're talking about faults that may occur during the normal operation of the system. Typically these are measured as radiation-based faults, single event upsets. They can be transient faults that occur through failures, through just normal operation of the system, aging and such. So we need to be able to inject those faults and measure how the system responds. That means we inject faults in some of the blocks you see on the left-hand side, see the faults propagate to the strobe point or functional output point, and then measure the time and response across the safety system, the checkers. So it's interesting, I presented this slide at NMI, and Infineon folks almost jumped out of the seat, yelling, saying we can't do comprehensive brute force fault injection on a microcontroller because the microcontroller folks don't have all of the software that the system people are going to put onto the system, so comprehensive, is difficult to do. The state space is absolutely enormous. So the focus there is the lockstep controller, more sampling within the microcontroller, and then measuring that the lockstep will respond correctly to any fault that propagates. And so the fault campaigns are going to be dependent on the design side, the design style that you have, and the way that you need to measure your system. But the final point that we want to make here on this slide is this is not like DFT. And so in design for test, we're going to look at manufacturing level faults. We're going to determine if those faults can be seen on a tester, and typically that's fault injection into the system and then measurement at pins of the device. Here the measurement may be inside the device itself, and it needs to be not just at the propagation point, but the safety system has to respond as well. And I'll discuss that here on the next few slides. So you can imagine this flow for fault classification. So for any given fault, we need to determine if the fault is going to exist in a safety critical part of the design or a non-safety critical part of the design. So again, a simple differentiation from DFT, which will check the entire device. If it's in the non-safety part, it can be classified as a not dangerous fault. Obviously, you want to increase your product quality, and so you'll be scanning for these, but that's a task that we can do primarily with DFT. If it's in the safety-related part of the design, we're going to need to determine whether this is a dangerous or a latent, whether this is a dangerous or a safe fault, and I'll explain a simple chart of that in the next few slides. But that includes whether or not the fault is going to be detected and corrected properly, or if the fault is going to propagate through the system and bypass or not be seen by the safety systems in a sufficient period of time. And this is the classification that we're getting to in a simple 2x2 chart. So the fault that we need to worry about is this one in the lower left-hand corner, in the red. So this is a fault that is propagating through the system. All right, so you're on the functional side, the fault does propagate, but the safety system fails to either observe the fault or fails to respond in adequate time. And the adequate time is decided by you as a designer. It is the fact that the system needs to respond quickly is specified in the standard. How fast is not. Right? So those details of what the checking systems are and how they need to respond is responsibility of the design team. It's not identified in the standard. It's just identified that these systems need to exist. Now, we could have in the upper left a fault that fails to detect, fails to propagate, and that's okay. So this is a fault that may be masked by logic in your design. So you can imagine an OR gate where one line is a value of 1, the other line doesn't matter what the value is. So the fault may be masked by logic, and that's okay. We can say this is safe and undetected and classified as such. Now, you may still have a question as whether the fault failed to propagate due to logic masking or due to poor testing. Right? So you need to make sure that you have proper stimulus. We'll cover that in the next couple of slides. Now the next set on the right-hand side, this is where the fault is dangerous and where the fault is dangerous and detected. That's the area that we really want to focus on here. And in that case, we can see that the, and I'll just focus on the lower right for sake of time here. If the fault is propagated through the functional system and detected, but the safety system responds properly, that's actually a dangerous detected fault, and that's okay, because that does not violate the safety, it does not break the safety requirements of the system. So yes, something did occur, and again, this is what we're all about. Your car is on the road 15, 20 years later, and a fault occurs. It could be a common mode failure, it could be a radiation-based fault, but did the system find it? did it respond properly, and put the vehicle into a safe mode of operation. That's what we're all trying to get to. So that's why, even though it's dangerous, it can still be classified as green because it's detected. Now, as you're listening, you're probably thinking, wow, this is huge. And you're right. Even for a relatively small design with 1 million gates of logic, you can imagine that the complexity is just enormous. So we really need to move away from brute force verification into more elegant functional verification, which puts us right into the heart of the team listening in here. Metric-driven verification to identify the functions within the system and provide a better functional campaign is absolutely critical to handling the complexity associated with safety verification. But you can also hear in this why safety and functional are tied. Because if you're going to build up that metric-driven verification environment, you're going to have a set of tests and you want to reapply those in the safety verification flow. So what does that mean? It means a common flow. So starting from a verification plan, we want to proceed through a metric-driven verification flow, injecting faults as we need, collecting faults effectively like we would with coverage, and then making sure that the system is safety covered as much as it is functional covered. And we should be able to use the tools that we have on the functional verification in the safety verification as well. Now that does mean the right side path. That means we need to create a safety verification plan, identifying the functional components from the safety components, the functional outputs from the safety outputs, and doing all of that measurement. And this system needs to operate certainly at a gate level, which is identified in the standards, but we're going to need to establish our campaigns at RTL, Verilog, and DHDL in order to build that campaign up quickly, again, due to the massive size of this part of the project. And we should use all the standard IEEE languages. We should be able to run in the context of mixed signal so that the design we're verifying around is the design at the end system. The less we do to modify the design, the fewer chances there are to inject errors or bugs into the system, and the easier it is to complete the compliance. So the closer we can stay to the actual system, the better we are. So ideally, we're going to gather all of this data together in some type of graphical flow because we'll have a broader team to look at this information. We're going to want to classify the faults that are detected, the things that need to be debugged, present this to the safety managers, present this to the design and verification teams, and have a single view of all of this data. Again, automating this where we can enforces that safety culture that we've just heard about and keeps all this information together and visible to the broad team. So just a small commercial at the end. So from the Cadence perspective, what we're trying to do in automating this is provide enhanced core technology for quality, performance, and integration to make sure that that functional and the full chain, this is not just digital verification, but it's digital implementation, analog design, analog implementation, board level. It really needs to be comprehensive if we're really going to embrace that safety culture. We need to innovate because we just discussed it very, very, very briefly. It's a massive verification problem. So we're going to need some new techniques in order to handle the just the sheer size of the verification challenge here. And we're going to need to work across the design chain, right? And that's one of the beauties of presenting in this DVClub is that we have people that are involved in all aspects of that design chain. Services companies, design companies, IP, the systems integrators, and more. So this is really going to be an industry-wide collaboration to make sure that we gather all the data, that we report properly, and that we're all in this safety culture together. So any questions, comments? I'm just a minute shy of my time.
Adam, we have one question.
Yes.
Online. It's from our friend Paddy. I think he's trying to prove he's not just here for the pizza. What is a transient fault? I didn't think the standard specified it, so what is injected?
Oh, very good. So the transient fault that is specified, this is a fault that can occur during the normal operation of time. I'm sorry, was there a change in the question? Or okay, so this can occur sometime during the operation of the device. Let's say it's been booted, a small operating system, you boot, you run, you're operating. We want to reach in and flip one of the bits in the system. It could be a state machine control bit, for example, and it will just change value from 0 to 1, 1 to 0 based on its existing state. There are two methods. There's a single event upset, which just changes it, and then it can change back based on propagation of signals. Or we're modeling an actual physical failure. Let's say there's a wire break in the system, and that would model as a transient that may be held for a period of time. So it could be held permanently from that time during the running of the system, or it could be considered momentary. That is, breaks and it's held for a microsecond and then released. But these are all potential faults that could occur in the running device. Okay, any other questions? If we had, I'm not sure if we have time.
Thank you. Thanks, Adam. Thank you very much.
Sure, and I'll stick through the end if there are questions at the end of the overall presentation.
Okay, thank you.